precipitation, we're going to use the ion product to determine if a precipitate will form or not. The ion product, which is Q, is defined the same way as KSP was, but we're going to use the initial concentrations, just like we described Q in chapter 13. So the yellow in the picture is a precipitate. Remember, mixing two liquids to make a solid is a precipitate. So just like before, if Q is greater than KSP, then a precipitate forms, and will continue to form until the concentrations are reduced to the point that they equal KSP. If KSP is greater than Q, then no precipitation will occur. So as an example, if we have too much silver ion and chlorine ion, then the reaction shifts to the left. Q will be greater than KSP at that point because our initial concentrations are too high as products. So the greater the Q or KSP value, the more products you have. So in this problem we have cerium nitrate and potassium iodate, and they want to know if cerium iodate will precipitate. So we're going to need to know our concentrations of cerium and iodate to start off with. So I'm going to write my dissociation equation for cerium iodate, which shows that I'm going to need cerium and iodate concentrations. Looking up at the top, I know my cerium nitrate concentration. And notice that my concentration of cerium nitrate and cerium are the same because it's a 1-to-1 ratio when that dissociates. Same thing for potassium iodate. My iodate and potassium iodate should be the same concentrations. So my cerium molarity is 4 times 10 to the negative third. I know my volume, so that's 750 milliliters. I can solve for millimoles. Or you could put liters in there and solve for moles, it doesn't matter. I'm going to do the same thing for my potassium iodate. So my iodate is 2 times 10 to the negative second. And I have 300 milliliters. So that gives me 6 millimoles. But I can't plug millimoles into my equation, I need molarity. So I divide by total volume. So that's 1,050 milliliters. Or if you calculated moles, then you would be dividing by total liters, which would be 1.05. I get my concentrations of each. And now I can plug it into my KSP expression that I had written earlier. Remember, Q and KSP are solved for the same way. So Q is equal to my cerium concentration times my iodate concentration to the third. So my Q is 5.32 times 10 to the negative 10th. Q is greater than KSP, so yes, a precipitate will form. And it will continue to form until the KSP and Q are equal. In this one, first you're going to need to assume that all of the magnesium and fluorine ions that can go together will go together to make magnesium fluoride. And then we'll see how much will break up in solution. This problem is different because we want to know the concentrations of magnesium and fluorine at equilibrium. We don't want to just know if it will precipitate. So first we need to find our concentrations of magnesium and fluorine. Magnesium is the same concentration as magnesium nitrate. So I can figure out my millimoles of magnesium. My concentration of fluorine is the same as sodium fluoride. So I know my millimoles. But unlike earlier, we're not going to get molarity first. We need to react them, and in order to react them, we need moles or millimoles. So magnesium and fluorine go together like so to make magnesium fluoride. We know the millimoles of each of them, and we're going to react them until one of them runs out, which will be magnesium since it's smaller. We don't care about the product because it's a solid and solids aren't in our equilibrium expressions. Once we get our millimoles after it reacts, we need to divide by total volume. So magnesium will run out and we'll still have 0.055 molarity of fluorine in the beaker. But not all of the magnesium and fluorine will go together to make magnesium fluoride, because very little of the magnesium fluoride is soluble. Most of it will form a precipitate. So we need to find out how much of the magnesium and fluorine will actually go together. So here we write our dissociation equation. And plug in those values that we just had, which was 0 and 0.055. So we assume all of it to have made magnesium fluoride, and now some of it will dissociate back out. Plug it into our KSP expression. We can ignore the plus 2x, but we can't ignore the squared on that. So we have x times 0.055 squared, and so our x, which is our magnesium concentration, is 2.11 times 10 to the negative 6 molarity. Our fluorine concentration we get from our equilibrium line, and that's 0.055 plus 2x, which is 0.055. So that's our concentrations at equilibrium. On this one, we're just seeing, will it precipitate? So pause the iPod, try that one on your own. When you have your answer, restart the iPod. You're going to need to look at your old note packet to find the KSP value. All right, let's see if you got it correct. So first you needed to figure out what your precipitate would be, which would be calcium fluoride. So I find my concentration of calcium ions, and then my millimoles, and then I find my concentration of fluorine, which is the same as sodium fluoride, and get my millimoles. Divide by total volume. And I get my starting concentrations. If you didn't get it earlier, the first thing you should have done was written your equation out. Sodium chloride is aqueous, calcium fluoride wasn't. That's how we got that we needed our calcium and fluorine ions concentrations. So our Q is equal to our concentration of calcium and 2 fluorines, which is fluorine squared. We know our concentration of calcium and we know our concentration of fluorine, so we can plug those in. Don't forget your square and solve for Q. Q is 7.41 times 10 to the negative 7th. You needed to look up the KSP value from your old note packet to find that calcium fluoride had a KSP value of 3.9 times 10 to the negative 11th. Q is greater than KSP, so yes, this reaction will form a precipitate.